So let us continue with what we were discussing in the previous lecture. We were trying to solve a problem of unsteady heat transfer, unsteady heat conduction using the lumped parameter analysis, and what we are trying to do is we are trying to figure out the temperature as a function of time, assuming that there is no temperature variation within the body as a function of position. Now when is that assumption valid? So we will try to answer the first question. So let us take this example. Let us say that you have a spherical ball with Tc as the center line temperature or central temperature, Ts as the surface temperature, and T infinity as the temperature of the surrounding fluid. So this is a solid ball. So you can write we can write not exactly equal because it is not a steady state problem. So the heat transfer due to conduction is not exactly minus Ka into delta T by L, but we can write order of magnitude wise whatever is the rate at which heat is being transferred here due to conduction, at the same rate heat is being dissipated by convection, and this is an approximate estimation of the rate of conduction heat transfer. Had it been one dimensional steady state heat conduction, that would have been exactly equal to this. Then instead of this order sign we could have put the equality sign, but here it is just the order because it is not a one dimensional steady state problem. So you can write there will be a here, right, a into h into t minus t infinity. So this a will get cancelled from both sides and you will get Tc minus Ts divided by Ts minus T infinity is of the order of HLC by K. What is this LC? We have not discussed what is this LC. This is called as characteristic length scale of the body. So typically the characteristic length scale is a length that describes the physical change or the change of temperature within the body. So you can see that in this expression that characteristic length comes out to be volume by area. So you can take it as a volume by area as the characteristic length. So here just to symbolize we have written it as LC without mentioning what is this LC. So this is a non-dimensional number, right? Therefore this is also a non-dimensional number. What is the name of this non-dimensional number? The name of this non-dimensional number is called as Bio number. Okay. So what does it physically represent? So the bio number which is HLC by K right. What is the numerator? It is the conduction resistance and denominator is the convection resistance. So it is a ratio of conduction resistance to convection resistance. Remember this K, very important, this K is K of solid, not K of fluid. We will later on see a non-dimensional number in the context of convection where it looks very similar, but the K is K of fluid and not K of solid. So now when can we think of that the entire solid is at a uniform temperature? When can we think of like that? We can think of the entire solid to be at a uniform temperature when Tc minus Ts is much less than Ts minus T infinity. That is, temperature variation within the body is much less as compared to temperature variation outside the body. So we can write if Tc minus Ts is much less than Ts minus T infinity, then temperature variation within the body may be neglected. This is zero dimensional model. So the model is valid. See, you cannot adjust this a priori because you do not know what are the temperatures. You cannot put these values and check. So what you can check this parameter. So this parameter implies that the bio number which is HLC by K of the solid much less than 1. So please do keep in mind that for the lumped parameter analysis to be valid, the bio number must be very small, much less than 1. Now question is, what is much less than 1? For all practical engineering purposes, see, for mathematical purposes it is in the limit as it tends to 0, but for all practical purposes the bio number may be considered to be small if it is 1 order less than 1, that is less than 0.1. So practically bio number less than 0.1 is good enough to make this approximation valid. So let us say that condition is true. Now what is the physical interpretation of the time constant? That is the first question that we would like to answer. Second question is, based on that physical interpretation, can we write it in terms of the bio number? Okay. So now the first question. Now look at it. Let us say that tau is small. If tau is small, then what will happen? See, let us say this is a lumped body. You create a change and this body is adjusting to that change in temperature. So question is, how fast it is adjusting or how slow it is adjusting. If tau is small, will it adjust fast or will it adjust slow? If tau is small, then for even a small value of t by tau is large, right? T by tau is large means e to the power minus large will be tending to 0. That means theta will be tending to 0. Theta is T minus T infinity. That means in a very short time T will come to T infinity. That means the solid body will very quickly come to the ambient temperature. That means the response of the solid body is very fast. So a short time constant means it responds to the temperature change very fast. And short time constant means what? Short time constant means short volume by area, small volume by area. Small volume by area means short small time. So small tau means small v by a. This means quick response. Why is it so? Because volume is what? Volume is the storage of thermal energy, and what is area? Area is the surface over which heat gets transferred. So if the area is much larger as compared to volume, then there will be rapid transfer of heat as compared to thermal storage. So V by A small means actually area much large as compared to volume. So then the body will quickly adjust to its change. So in other words, in this quenching example, it will cool fast if V by A is small, right. So if V by A is small, it will cool fast. On the other hand, if tau is large, then what will happen? If tau is large, then for a short time it will be what? E to the power 0, right. If tau is large, then for a short time a small number, a short time divided by a large time, so that means it will tend to 0. So e to the power 0 will tend to 1. That means theta will tend to theta I. That means the temperature of the solid will remain same as the initial temperature even for a substantial time. The change will be slow. Clear? So we can say that tau is an indicator of the rate at which, the time rate at which the body adapts to a thermal change. If it is small, it adapts quickly. If it is large, it adapts slowly. So now how can this be applied? This can be applied to many engineering design problems, including say the design of a riser in a casting system. So in a casting process, you know that there are shrinkages at various levels, and when there is a shrinkage during solidification, what will happen? So there will be a volume that needs to be replenished, and the riser is there as the supply of the molten metal, which will supply to the mold till the entire mold solidifies. That is the requirement of a riser in a casting problem. So when you are having such a requirement, the riser should solidify at the last, because it must supply the molten material to the mold till the final mold solidifies. So riser must solidify last. So that means riser must lose the heat most slowly. So if the riser must lose heat most slowly, then the time constant of the riser must be large, right. That means volume by area of the riser must be greater than volume by area of the casting, because its time constant should be large, so that it should respond slowly to the thermal change, so that it will not immediately freeze. This in riser design problem is known as Vorinov's rule. So there are, see, classically manufacturing process or studies in manufacturing in many cases have been experience based. So before the science of this was properly known, people from experience found that this should be the case for the riser design. So now you can see that the rule bases which are taught in manufacturing processes can be fundamentally derived if you think of a mathematical analysis following heat transfer. Okay. Now how can you apply it for a practical problem? Let us say you are measuring the temperature of a body with the aid of a thermometer or a thermocouple. What kind of thermometer or thermocouple will you want? Something with high time constant or with low time constant? In that case you want a low time constant, because you want the thermometer to quickly adjust to the temperature of the body with which it is in contact, right? Otherwise it will take a long time for it to read the actual temperature. So when you go for purchasing of a temperature measuring instrument, you should look into the time constant and make sure that the time constant is small. Then how can we write this AH by rho CV into T? So tau So you can just manipulate the algebra and you can write T by tau in this way. So T by tau is T by rho C into LC by H, LC is V by A, okay. So now you can multiply by K. Why you multiply by K? Because you want to get the bio number HLC by K. So this is a non-dimensional number. We have discussed about its physical significance earlier. This is also non-dimensional. That means this is also non-dimensional. This is called as Fourier number. So how do you define Fourier number? Fourier number where alpha is the thermal diffusivity, alpha is K by rho C, that is the thermal diffusivity. So this can be written as T by LC square by alpha. What is this? If this is unit of time, this is a non-dimensional number, this is also a unit of time. This is called as diffusion time. Diffusion time is a time over which heat diffuses over a given length. So the time over which heat diffuses by a length LC is LC square by alpha. Okay. So we have studied the lumped parameter analysis for a limiting case when conduction is dominating. We will consider the other limiting case briefly before working out a couple of problems. The other limiting case is when radiation is significantly dominating over convection. Radiation is significantly dominating over convection. So let us look into the governing equation. This equation, which we derived in the previous lecture. Now this term will not be important as compared to this term. So you can write rho CV dt is equal to minus A sigma epsilon T to the power 4 minus T infinity to the power 4. Okay. So this is also a very straightforward problem. In the previous case the integration was dx by x. Now the integration is of the form dx by say a to the power 4 minus x to the power 4, right. So I will not go through that, but I leave it on you as an exercise, but very simply you can do that. This you have done in school level. So integral of this is the form of the integration. A is t infinity, this is t. So you can write this as integral of dx by a square minus x square into a square plus x square. So this you can write integral of 1 by 2 a square plus x square minus plus a square minus x square. Again for this term you can write a plus x into a minus x, and numerator you can write 1 by 2a right. So one of the integrals will be ln of a plus x, another will be ln of a minus x, and this if you substitute x equal to a tan theta, it will be a straightforward integration. So the integration is quite easy. Even if you do not remember any formula, you can reproduce it quickly. The remaining part of the problem is just purely algebraic simplification. Concept wise we do not learn anything new. So we will work out a couple of problems related to the use of the lumped parameter method, and we will start with working out the problems. So the first problem, please note down the problem. This is a problem from Incropera's book. Steel balls of 12 millimeter diameter, steel balls of 12 millimeter diameter. So D is equal to 12 millimeter, this is 2R, are annealed are annealed, annealed means annealing is a heat treatment process, are annealed by heating to 1150 Kelvin, are annealed by heating to 1150 Kelvin and then slowly cooling to 400 Kelvin. I am repeating, steel balls of 12 millimeter diameter are annealed by heating to 1150 Kelvin and then slowly cooling to 400 Kelvin. In an air environment for which T infinity is equal to 350 Kelvin, so T infinity is equal to 350 Kelvin, H is equal to 20 watt per meter square Kelvin. Assume K of the steel is equal to 40 watt per meter Kelvin. Rho of steel is equal to 7800 kg per meter cube. C of steel is equal to 600 joule per kg Kelvin. Calculate the time required for the cooling process. How much time it will require to cool? So, what is the final temperature? Final temperature is 400 Kelvin, right? What is the initial temperature? 1150 Kelvin. So, we can straight away use the lumped analysis, provided we justify that the lumped analysis is valid. So, for solving any problem using lumped analysis, first you have to calculate the bio number and then tell. So, what is the bio number? HLC by K. What is LC here? Volume by area. So, LC is volume by area is equal to 4 by 3 pi r cube by 4 pi r square. Okay. So, if you calculate this, this will come out to be, if you substitute the values, this will be 0.001. Sorry, not the LC, the bio number. Okay. So, we can assume this to be much less than 1. That means lumped analysis is valid. So, then we can write the governing equation and solve the governing equation. I have already done it. So, I am not going to write it again, but I will just write the final solution. So, theta by theta I is equal to my e to the power minus AH by rho CVT, right. What is theta? T minus T infinity, and theta I is equal to Ti minus T infinity. So, in this expression you have to find out what is the time. So, you can take log of both sides and find out what is the time. So, log of both sides and what is the time. So, the answer I am giving, T is equal to 1122 second. This is a straightforward use of the theory that we have discussed in the class. Now, let me ask you a question. For the lumped analysis to be valid, is it necessary that the bio number has to always be small? See, why did we impose the condition of bio number small, we wanted to make sure that the entire body is at a uniform temperature, right. Let us think of a situation, let us say that you have one glass of hot milk and the milk is slowly stirred by a spoon. Because of the stirring of the spoon, stirring with the help of the spoon, the entire milk will come to a uniform temperature, close to practical purposes. So then whether the bio number based on the volume and area is small or not is not important, because we have ensured by stirring that the milk is at a uniform temperature. So the requirement of bio number much less than 1 is not a fundamental requirement. The fundamental requirement is the uniformity of temperature. So we can say that bio number much less than 1 is a sufficient condition for lumped parameter analysis to hold, but not a necessary condition, right. If it is true, then the lumped analysis will be valid, but even if it is not true, but the substance is homogenized to a uniform temperature, then you can use the lumped analysis. Now can you tell that why I was telling that the milk is slowly stirred? If the milk is stirred very fast, then convection within the fluid will be important, convection within the system is important, and here we are assuming that the convection is taking place outside the system. Within the system it is pure conduction. Okay. So conduction analysis will not work for a system where, because of very vigorous stirring, convection within the system is itself important. Then you have to solve the fluid flow equations. Okay. So finally we will work out another problem and call it a day today. So that is the last problem that we are solving today. So the problem statement is like this. This is also a problem from the exercise of Incropera's textbook. So you have a long wire of diameter is equal to 1 millimeter. It is submerged in an oil bath of T infinity is equal to 25 degrees centigrade. Electrical resistance per unit length is 0.01 ohm per meter. The current that flows through the wire is 100 ampere and the convection heat transfer coefficient is 500 watt per meter square Kelvin. The first question is, what is the steady state temperature of the wire? This is the first question. Second question is, from the time when the current is switched on, how long does it take for the wire to reach a temperature within 1 degree centigrade of steady state value. Other properties are given. Rho is equal to 8000 kg per meter cube, C is equal to 500 joule per kg Kelvin, and K is 20 watt per meter Kelvin. Okay. So, the physical problem is that there is a current which flows through a resistance, so there is a joule heating. Because of joule effect there is a heat generation and that heat is dissipated to the surroundings. At steady state the rate of heat generation is same as rate of heat dissipation to the surroundings. But during unsteady state what will happen, the temperature within the wire will change with time before achieving steady state. So, the first part of the problem deals with the steady state, second part is the unsteady state. So, we will write first develop the general formulation and then we will apply it to both steady state and unsteady state. First of all, before applying the unsteady state situation, can we use the lump model here? So, let us say that length of the wire is L. So, the Bayer number HR by 2K. Okay. So, if you substitute these properties, this will be 0.006, this is less than 0.1. So, it is a sufficient condition for the lumped parameter analysis to be valid. So, now let us try to make a control volume analysis of this electrical wire. So, energy in minus energy out plus energy generated because it is a lumped body we can write ddt instead of the partial derivative. Okay. So, what is the rate of energy in? There is no rate of energy in. What is the rate of energy out? So, there are two modes, convection and radiation. We assume that convection is the dominant mode as compared to radiation. So, minus AH into T minus T infinity plus what is energy generation? I square R. So, because R I have used already for radius, so I am using a different symbol RES, resistance, okay, is equal to So we can write what is A? A is 2 pi R L into T minus T infinity plus I square. Now resistance is given, see Re dash per ohm per meter, this multiplied by the length will be the total resistance. So I square Re dash into L is equal to rho C pi R square L into dt. Okay. So L gets cancelled from both sides. It is given that it is a long wire, otherwise it will not be a one dimensional problem. In fact, one dimensional here becomes 0 dimensional, it is not even one dimensional, it is a 0 dimensional problem. Now all the values are known, so what is the first part? What is the steady state temperature of the wire? So steady state temperature of the wire is obtained when this temperature stops changing with time, then it is steady state. So when this term is 0, then generation balances heat loss. So left hand side equal to 0 will give the temperature, the steady state temperature. So minus 2 pi R into T steady state minus T infinity plus I square R E dash equal to 0. This will give you what is T steady state. So if you calculate this, so T steady state will be 88.7 degrees centigrade. Now what will be the unsteady state variation, because for the second problem basically you require to find out temperature as a function of time, right. So if you look into the differential equation, the differential equation is of the form of this form, right, where P and Q are some coefficients. This is the form of the differential equation. So for solving this differential equation, you have to multiply with an integrating factor e to the power integral p dt. That is the integrating factor by which you have to integrate. So if you do that, it is a straightforward solution of the differential equation. Okay. So let me give you the solution to the problem. T minus T infinity minus okay. So this is the solution to the equation. Now you have to find out the time at which this temperature becomes 1 degree less than the steady state temperature, right. So the steady state temperature is 88.7, so that will be 87.7. And then you take log of both sides and find out what is the time. The answer is 8.31 second. Okay. So, you can complete the calculations, but you have understood the method of how to solve this problem. So, to summarize, we have mainly discussed today about first some aspects of lumped parameter analysis, and then what are the conditions under which the lumped parameter analysis works, and we have used the lumped parameter analysis to solve a couple of problems of practical interest. Okay, thank you very much. Let us stop here today.